Chapter 5, Transform Analysis of LTI Systems. Transform analysis means frequency domain analysis. We have already talked about LTI systems and the frequency domain earlier. In this chapter, we will look at LTI system in frequency domain from different aspects, and we will look at some special LTI systems. One aspect of LTI system we are going to look at here is the phase response. For example, Hn is delta n minus 2. The frequency response is this one, and the phase can be represented this way. But we know the phase function is not unique, and we can have different representations, and we have talked about two particular representations. So one is ARG HEJ omega. It has the principal value of the phase function. So you constrain the phase function to be between minus pi and pi. And the other one is a continuous phase function. And we have the small ARG. So with the big ARG, we draw the phase function between minus pi and pi to be between minus pi and pi. And so when we draw minus 2 omega from 0 to pi over 2, the phase goes from 0 to minus pi. And because we wanted to constrain it between minus pi to pi, we move this section here to here, because this doesn't make a difference in the actual value of h. And similarly for this part, it's minus 2 omega, the function minus 2 omega, and continue on. But now we move this part to here, and this is big ARG. And with the small ARG, we simply draw it as a continuous function of h. This continuity of minus pi to pi like this, discontinuity of 2 pi like this. And in this particular example, the small ARG function, we see that it's a straight line. It's a straight line like this. So it's actually a linear function of omega. In this case, HEJ omega is said to have a linear phase, okay? Because the phase function is linear. In some applications, it is preferred to have a linear phase. But what's wrong with a nonlinear phase? We will look at a particular case where phase matters. Let us first define group delay. Group delay function tau of omega is a function of omega. It's the derivative of the phase function, with a negative. And the unit is in samples. We will see why the unit is samples later. With the definition, we can see one connection with a linear phase here. When H has linear phase, we will often abbreviate it with a linear phase. We will be using this a lot. If H has a linear phase, then what would be the group delay? When the phase is linear, it's a line. And when we take the derivative of that, it would be a constant. So the group delay function is a constant if H has linear phase. In other words, if H's phase is not linear, then tau is not a constant. So this group delay can be used as a measure of how nonlinear the phase function is. So the deviation from constant will indicate the degree of nonlinearity of the phase. How nonlinear the phase function is, that would reflect on the group delay. We will see how non-constant it is. It will give us a sense of how nonlinear the phase function is by looking at the group delay and see how non-constant it is, the deviation from constant. To see the kind of role group delay play, we will look at one particular example. In this example, we have an LTI system H, and we have an input. The input is Sn, and an exponential is the product. And this Sn here is a very narrow band, low pass signal. So in the frequency domain, that's what S look like. It's very narrow band and it's low pass, so it's a narrow band signal. It's concentrated around 0 frequency, and Sn is the product of S and an exponential function. We know when a signal is multiplied by an exponential function in frequency domain, it will get shifted. So originally S is centered at 0. Now X would be centered at omega 0. And omega 0 is the frequency of this exponential function here. When such a narrowband signal is passed through the system, the LTI system, which part of the frequency response will matter to the input or matter to the final output? When a signal is passed through an LTI system, the output Fourier transform is the product of X and H, right? So since X is such a narrow band signal, what matters to the output would be the frequency response of H around omega 0. So let's look at the part of H around omega 0. Let's say at omega 0, the slope of the phase function, the slope is negative ND. ND is the, we just say ND is some number and slope is the negative of ND. And since the group delay is the derivative of a phase with a negative, the derivative of phase over minus ND, and phase has an extra negative, so it's just ND. Or we can say that the group delay function is the negative of the slope. Now we can approximate the phase function around omega 0. At omega 0, the slope is minus ND. Around omega 0, we can write the phase function as approximated. Around omega 0, we approximate it as a linear function because the slope is minus ND, so we have minus ND, omega minus omega 0 plus theta, where theta is the value of the phase function at omega 0, and this approximation is valid for omega around omega 0. Now we can merge the two constant terms with minus ND omega here and a constant term ND omega 0. We can merge it with theta and let's call it phi. Now let's use this approximation and let's see what we are gonna get at the output. Around omega 0, the magnitude, we have H and X, right? And around omega 0, the magnitude of H is the magnitude of H here. And then the phase, that's substituting the phase function approximation. We have this phase that is minus ND omega. And also EJ5 here, and then X. We know when X EJ omega is multiplied with a linear phase term here, like so, in the time domain, it's a delay. So Xn will get shifted by ND. So we have S. If we apply inverse Fourier transform, we get Y. And we apply inverse Fourier transform of this term here, we get S shifted by N, X shifted by ND. So we would have S shifted by ND and the exponential function shifted by ND. And these two terms are simply constant, a constant here and a constant here. So what is the role of group delay? When we apply a narrowband signal like this, the narrowband signal will get shifted by ND by so many samples. So that's why the definition. Why the definition of the group delay, the unit is samples. And when we have a narrowband signal that's passed through an LTI system, it will get delayed by so much by ND. And there's also a constant term that's equal to the magnitude of H and EJ5. Using a simple approach, we can show that when H is real and X is Sn cosine omega 0n instead of Sn ej omega 0n, then the output Yn can be approximated as h ej omega 0 Sn minus nd and a cosine term that's also delayed by nd and then with an extra phase. Suppose we have an xn that looks like this in the time domain. Here we have around 200 samples, and first is fast varying like this, and now it's going much slower and then faster again. You can think of it as a concatenation of three signals. The first one, that is x1. This part is x1, the fast varying one. And then x2 is this part, the slowly varying one, more slower. And x3 kind of in the middle in terms of frequency between x1 and x2. If we take the Fourier transform of such an xn and we plot the magnitude spectrum, this is what we get. It has a peak around 0.3 pi, maybe. It's centered around 0.3 pi. And then there's another piece that's centered at 0.5 pi. And another chunk centered at maybe 0.85 pi. Okay. This is from 0 to pi. And it's a real sequence, so if we look at the magnitude spectrum, it's symmetric. So if there's one peak at 0.85 pi at the symmetric place, there's another peak. And if there's a peak at 0.5 pi at this place, at the symmetric place, symmetric frequency, we have a piece that's centered here. And then also one piece here. And if we just concentrate on the 0 to pi part, we can relate these peaks with x1, x2, and x3 here. For example, x2 is the slowest varying one, so we can expect that x2 would give rise to a peak here. This peak should correspond to x2, whereas this peak here will correspond to x1, and this peak here will correspond to x3. So x is a concatenation of three sequences, and each sequence can be viewed as the type of signal that we just talked about. It's a low pass and shifted in frequency. So for example, this is a low pass and it's a shifted frequency so that it's centered around 0.3 pi. And this is a low pass, but it's shifted to the frequency 0.5 pi. And this is a low pass shifted to 0.85 pi. Now we are going to pass such a sequence through an LTI system. Remember, the peaks are centered around 0.3 pi, 0.5 pi, and 0.85 pi. So the magnitude response of the LTI system at these 3 points would matter, and the phase, the group delay of the system at these 3 frequencies would matter. Now here is the H. This is the magnitude response of H. It's symmetric, so symmetric with respect to pi. So we can just look at the magnitude response from 0 to pi, and we can see that it's, what kind of filter is it? Low pass, band pass, high pass? It would be a low pass filter, but the pass band is wide and it drops down at about 0.05 0.6 pi, and between 0.6 pi and pi, this will be the stop band. The red dot, green dot, and the blue dot here will correspond to the three frequencies that the magnitude response of H at the three frequencies that we talked about earlier. So for example, this is 0.3 pi, this is 0.5 pi, and this is 0.85 pi. And we can see that at 0.3 pi, the value of H magnitude response is quite close to 1 because this is dB. So 0 dB will correspond to the value 1. And similarly, for the green dot, the value of H magnitude is close to 1, but it's a different story for the blue dot. Here it's almost 2, minus 100 dB. So now we have the red, the green, and the blue dot. There are 3 peaks in the Fourier transform of X. Are we still going to have 3 peaks after we pass a sequence through H? Do we? We can see here the peak at this frequency will get so much attenuated because minus 100 dB is a lot of attenuation, so this will get attenuated. So we can expect that later on in the output we can only expect this peak, the peak at center at 0.3 pi and the peak center at 0.5 pi will go through the system, but the peak here will be almost eliminated by the system. Now let's look at the plot of group delay. This is group delay of the system, and so we look at the group delay at 0.3 pi, and the group delay here is around 200. The group delay for omega equal to 0.5 pi is around 50. So x3 here will get delayed by approximately 50 samples, whereas x2, the group delay here is 200, so it will be delayed by approximately 200 samples. Here's the output. For x2, the group delay corresponding to the center frequency of x2 is around 200, so it gets delayed by about 200. Whereas x3 was actually after x2 in the input, but now because the group delay corresponding to the center frequency of x3 is around 50, so it gets delayed less. So in the output, we see that x3 appear before x2 now. And at the output, we no longer have x1 because it's attenuated by the system too much that it's just not visible from the figure. So with a nonlinear phase system, signals corresponding to different frequency would get delayed by different amount, and this will not happen with a linear phase system because all the signals will get delayed by the same amount, by the same number of samples. And from here we can also understand why the unit in group delay is samples, because it represents the number of samples that a narrowband signal will get delayed when the narrowband signal is centered at that frequency.